So if DLSS has 5 been definitely not horrible, I'm sure it can do better. My first idea goes as follows. My program takes the image and for the added pixels just chooses the average of the surrounding original pixels. And of course I wrote this in everyone's favorite language for performance. Yep, putting an image in takes forever for it to finish. And then, turns out I just made a very crude blurring algorithm. Let's quickly move on from that to a better idea I had a couple months later. I take the image and get its dimensions. Then I create a rectangle for the output image with the doubled x and y sizes. After doing so, the program loops through the list of yet-to-be pixels and uses rounded division to find out where approximately the closest pixel from the original image is. In a try-catch block, in case of indexing issues, we look up the pixel value for each of the 4 surrounding pixels and do a quick check whether all of them are transparent. Following this, we found out the distance between all colors using the formula d equals r2 minus r1 all to be squared plus g2 minus g1 all to be squared plus b2 minus b1 all to be squared, taking the square root of all of that. Then, using this line of code, which I do not want to need to figure out later, we get which of the colors has the lowest distance value assigned, or in other words, which color is the closest to the rest of them. And using this switch statement, because I am not a great programmer, we then find out which color that actually is and assign it to a new pixel. However, you are likely already screaming at me that this only upscales the image once by 2 times and nothing else. Now this is true, so I added a little function which takes in the original image and the scale factor, which works more like an exponent than a scaling factor, and then for how many times the exponent says, repeatedly puts the image into the algorithm to finally return this image. Now let's see how this works. Let's take this image again and drop it in. Well, it most certainly is not blurry anymore, so that's a positive. Well, I guess that's that finished. I guess now all that remains is editing and...
Isn't there something you have forgotten?
Wait, what?
This is written in Python, the language of the weak, the language that should not be used for a final product. Have you betrayed your own beliefs?
Must I? Isn't this just a proof of concept? I don't have to write this well, right?
You have the choice. Betray your beliefs or do what is right.
Ah, jeez, I guess I'll write it in C. Well, let's set this up. We compile with GCC, STL image for drag and drop, and it compiles from the 2 files upscale.c and main.c. Let's create those. Oh yeah, and I also need an upscale.h file. Now let's get some functional default STL starting point. With drag and drop, of course. Now, as I should have expected, doing this in C is quite a bit more difficult. For instance, did you know that I can't just read the pixel value from a texture, as it is technically only on the GPU, so I have to also pass the surface of the texture into the function instead of just reading the pixel from the texture. I didn't know this until I read this thread on the STL forum. Did you know that STL has a forum? Well, actually, I can read a pixel from a texture. However, according to this person, reading from a texture can absolutely destroy rendering performance. Surfaces are to be used CPU side, textures are to be used GPU side. Although, according to the direct reply, the pixels made available for editing don't necessarily contain the old data. This is a write-only operation, which I was able to tell did cause issues. Okay, I guess I will be keeping the surface around. Now after some more stuff in my commit history, I found the commit titled Oops. I remembered that something funny or interesting happened with this one. Yep, I can only disrupt this one with Oops. But anyways, keeping the surface around actually seems similar to what I do in the Python version, where I keep around the rectangle, which I believe is just a different name for the same thing. A difference to Python, however, is that I can't just easily create a list of 2 different types. What I instead need to do is create a struct for the 2 types and use that as the return type. Next, I just need to create the surface to return and return it with the texture, and after I create a small function to recursively follow the upscale function, so I can have a bigger than just 2x scaling, I was finished. Now, whilst I was creating this, I was wondering whether I should share some form of benchmark, as I feared that due to my lesser skill, I might have screwed up the C version so badly that it would be slower than the Python version. However, when I went to actually test the 2 versions on the same image and same scaling parameter, it turns out my fears were completely unjustified. However, before I will show you these results, there are some minor issues I have discovered. When I was trying to fix a last issue, I noticed just after this, I was first struggling to drag and drop the image file into the application ever since I switched compositor again. But running the program with the environment variable of stl_window driver set to Wayland, it worked again. The Python and C versions need a different scaling factor for the same results. To be more precise, the Python version needs its scaling factor to be 1 higher than that of the C version. This was a very odd issue, as when I was trying to debug this, it even confused the read-only LLM agent I was utilizing to try to figure out why this was leading to hilarious occurrences such as this one. Isn't it funny when an LLM, which is supposed to take your job in 3 to 6 months, believes that 4 is equal to 8, although to its credit, it did realize that that does not make sense. Although the fix ended up being quite easy, the problem was just that in my recursive function for the C version, I was returning the result of upscaling it again, whilst in Python, I wasn't. Just a very quick fix. The pixels at the top and left look weird. I don't know what to do about it, however, as it isn't all that severe, I will just ignore it. Now, I'm sure there are further issues beyond these, however, I would just like to finish this project now. But before I can do that, it is time for a benchmark. Just a quick disclaimer. There is no guarantee that this is a fair benchmark and should be taken as precise language performance comparison. Whilst I've done my best to make the code logic be identical, with the only differences being incurred by the languages themselves, it is impossible that I executed this aim flawlessly, as it is clear by the slight discrepancies seen so far. These results should be taken for an approximate comparison and to no further degree of importance. With that out of the way, it is time for me to actually figure out how to do a benchmark. Using this really nice guide from Geeks4Geeks, I was able to set up some values for how long the individual parts take. All the tests have been made with the same 32 by 32 pixel image of some random colors I had created around half a year ago to test this algorithm, and the first proper run from the C version produced these results. We can see that at a scaling factor of 8, the algorithm takes approximately 4.37 seconds to complete. Running the same procedure once more, we get this slightly different result. We can see that the time it takes the computer to process the insertion of the image takes 3 what I think is microseconds longer than the last, which is very much negligible. Apart from that, the image processing takes 27.574 milliseconds longer than the previous time, which can be led back to various unpredictable factors such as background load on the PC during the tests. The reason for the multiple runs is to get a better average than a single test, although at these small areas of results, these millisecond differences are sure to be mostly irrelevant. Running the test one final time, the insert time decreases by 1 microsecond from the last test, and the upscale time has increased to almost 4.6 seconds from the 4.37 seconds in the first test, showing a jump by almost 223 milliseconds, still below the average human reaction time. Now let's test the Python side. After adding some rather simple code on the Python side as well, here's the first result. We can see that the time for the processed image insertion is marginally smaller, although similarly to the skews in the C version, this is likely to be traced back to minor differences in background system load. It is clear, however, that the time to upscale has drastically risen from the highest in the C version at almost 4.6 seconds, the Python version taking almost 94.1 seconds. The second result shows a similar picture. The image insertion time being marginally different and the upscaling time still being around 95.25 seconds. In the third test, we for some reason see the image insertion time rising to 9 seconds. This is peculiar, however it doesn't seem to be a pattern, so it should be ruled out. Apart from that, the only difference is that the upscaling time is about 2600 microseconds higher than the previous test. Now, as much as I would love to go on a side quest and create a benchmarking system that does 100 tests per version per scaling factor and creates graphs and all that stuff, I think that would have to wait for another project. So for now, the conclusion we can quite safely draw from these benchmarks: Python's slow, like really slow. If you want to screw around with this stuff, I have left the repo in the description. The code is highly documented if you are interested in understanding it. Furthermore, on the use of AI, or as it correctly should be called LLMs, in this project, I have in the second attempt, Python and C version. The only way in which they have been used is for analyzing the code to see what is causing certain errors and bugs. Neither of them have any generated code. As for the first attempt, I don't have a clue, as it is around half a year back. Now finally, I want to sincerely thank you for watching till the end. If you enjoyed listening to me talk about some of my projects, you will likely enjoy my last video, which covers my participation in the 14th Goodware Game Jam. If you want to support my content, then it would massively help me out if you were to like this video and leave a comment. Thank you.